Okay, 10.3, inferences for correlation and regression. Just remember that when we have a sample, we're talking about statistics. When we've got a population, we're talking about parameter. So in this case, we're talking with our calculators, we get an R value out of those. That's actually the sample for rho. That's the Greek letter rho. That's the population parameter. For correlation coefficient, your sample statistic A is alpha. It's the y-intercept in your line of best fit. Your B is got a beta that goes along with that, and beta is just the population slope for your line of best fit. You got this y hat, and then you got y that's got no hat above it, which is your population line. So, some inferences: the sets of ordered pairs x and y constitute a random sample from all ordered pairs in the population. So in other words, we're grabbing ordered pairs from this particular population for which the fixed values of x and y follow the normal curve. Okay, that's kind of a big one there, because if we know they follow the normal curve, we can use z-scores and whatnot to figure those out and find the areas and probabilities of things happening. So all distributions for all y values have equal variance and a mean that lies on a regression equation. Okay, so first thing first, we're going to test the correlation coefficient. So just like any hypothesis test, we'll have H naught, which means the null hypothesis. We're going to test the correlation coefficient, which is R. So its rho is 0, and that's saying is that there's no linear correlation whatsoever. You've got your three possibilities for alternative hypothesis. It could be greater than 0, less than 0, or different from 0. We can convert student's t distribution, or we're going to use student's t distribution in this case. Your sample size has to be bigger than 3. Now that's only because in order to have any sort of correlation coefficient, you need to have at least 3 ordered pair. Now, a little bit different, your degrees of freedom aren't going to be n-1 now. They're going to be n-2, and the way I think of it is we're dealing with x comma y, so that's 2 variables. So you end up subtracting 1 twice, and you get a degrees of freedom of n-2. Okay, R comes from your calculator, n is the number of ordered pairs. So here we go. Let's grab some data and start doing some of that. Just a quick refresher. Hypothesis test means we've got null hypothesis, alternative hypothesis. We'll get a t-score. We'll look up the p-value using the table. We'll compare the t-value and either reject the null hypothesis or we will not reject the hypothesis. And then we'll make some sort of statement or conclusion based on that. Okay, so here's some data. Took this out of the book. X is the percent of population 25 or older. So Y is the percent of growth per capita in income. It's talking about the relationship between the years of school and a particular person's income. So in this one place or one town, 9.9% of the population was 25 or older, and their percent growth per capita income is 37.1. So context of the problem, we'll kind of talk about those things. We're going to test at a 1% level of significance the fact that we believe because rho was 0.887, which is positive, that rho is actually bigger than 0. Okay, so I'm going to, again, go through, find a t-score. So you can kind of see where I plug those numbers in, get that t-score 3.88. Go to the table, notice it's between those two t-scores, so therefore I've got a p-value that's between 0.5% and 1%. Remember, it was one-tailed. So make sure you go back and look at the one-tailed. Now, since we're testing at an alpha that's less than 1%, we've got a p-value that's smaller than that. So we're going to reject the null hypothesis that there's no correlation, and we believe that at 1% level of significance, there's actually a positive one. Okay, so that's kind of that. Standard error. So standard error is kind of like the standard deviation for all this stuff. I'll show you the formula, and I'll show you some other stuff too. But standard error has an S with this little sub E, letter E. Again, it's come from more than 3 ordered pairs. It's kind of the same procedure to get A and B line of best fit. It's the standard error that's involving that line of best fit. But you see it's the summation of y squared, summation of x, y, and things like that. I'll show you how you can compute that. I'll basically tell you this. Use your calculator. So L1 put in all the x values. L2, put all of your y values. Go to stat, but now we're going to go over to test for the very first time. And scroll down, it's close to the bottom. It's E, linear regression t-test, or linreg t-test. It's going to have an S. It won't have that E below it, but know that S of 3.77 is your standard error. Okay, so if I went a little fast on how to go through and type that, just kind of pause it, type those things in, run through it, make sure you get that standard error of 3.77. Because that standard error is actually a number that is in the formula for testing B, or slope. Now, correlation and slope are kind of related to each other, but they're not exactly the same number. Same thing for the other hypothesis test. Our null hypothesis is going to be there is no slope, and we've got your various alternative hypotheses. Once you've got those all figured out, you can figure out the t-score, and here's the formula for the t-score. Again, the degrees of freedom is going to be n minus 2. We're going to use student t's to get the p-value, and we're going to reject or accept it depending on, or fail to reject depending on how it relates to alpha. And then, of course, state some context towards your application. All right, so here we go. Same data as before. Hopefully you got that into L1, 2 also. You got L2 also in your calculator. We're going to test that at 5% significance. That beta is not actually 0, that it's something different. Again, you can put in those respective values for t, but I'm going to ruin the surprise. If you run linear regression t-test, and this is actually the case for the last one, that t value is going to show up. In fact, that formula for t with the r, or rho, it looks different, but it ends up calculating out the same 3.84. So I would suggest going straight to your calculator, getting it from there. You don't have to worry about messing up any of the calculations. But the only thing I would do is I'd ask you to put in the respective values there, just so I know that you put in the right spots. So you got that t value. It's in between the two t-scores in the table. Your degrees of freedom, again, are going to be 6 minus 2, so 4. So your p-value I got was between, let's see, 1% and 2%, and we're testing at 5%. So we are going to, again, reject the null hypothesis that there's actually going to be a slope. We just said we're testing different than, so the t-score was the same, but the p-value was different because we should be looking underneath the two-tailed table, or row in that table. Okay, correlation coefficient for y. You've got your population regression equation with some sort of standard error, and that standard error is going to be a lot like what we did with all our other confidence intervals. Remember, our confidence interval was something like I got an average minus the error and an average plus the error, and our population mean was somewhere in between those. What we're going to be doing is that for y. So just go through real quickly what it takes to get a confidence interval again. Again, you need 3 points. 1 and 2 are pretty much the same. Here's our error formula. Now, unfortunately, this is one of 2 formulas that we actually have to work out by hand. We can get those values pretty quickly from our calculator and plug those in. We have a C, a confidence level, so I want to be like 95% confident. So TC is different from T, and then we'll take our standard error that we just got from our calculator. So back to the same data again. You've got your degrees of freedom of 4. Okay, I'm going to look up T of 0.9, so 95, because I'm 95% confident. Now that's going to look a little bit different because now I use the table the old school way and get 2.776. Okay, oops, gotta go back there. One thing that's different is it's going to say find a 95% confident interval, but it's going to say for some x value like is equal to 10. Now what that means is I have to take my line of best fit from before, go back. Y is equal to 10.1 plus 2.55x. This 10 has to go in for x, and I get a value for y hat that I can use as my point estimation, or my number that I'm going to add and subtract my error to. I got my 2.776 for that. Remember, my standard error was 3.77. The square root of 1 over 6, because I got 6 ordered pairs. Oh, I forgot about the 1 plus 6 parentheses. Now that x is going to be what I plugged in for x here, and that's 10, minus the average of x bar. And I know I didn't talk about where to get those, but I will here in a second. Divided by 6 times 740.68. Take away 65.2 squared. Now, I am going to use the 2var stat and to get my x bars, my sum of x, my sum of x squareds. That's also going to show me my y bar, sum of y, all those lovely numbers that I might need to plug into there. Okay. When I work that out, and I like to work this fraction top to bottom, add the 1/6, add 1, take the square root, then multiply, I get an error of about 13.4. So my y hat minus the error, my y hat plus the error, and there's my confidence interval for y. And I end up getting 22.18 and 49.01. So I'm 95% confident that y is between those two numbers. Okay, so a confidence level for beta. Again, it's going to be pretty similar. It's going to be the exact same process. Did a different formula for error, and like I said, this is the second formula that you'll actually have to calculate out by hand. Isn't going to be able to be done with the calculator. So I'll pull from linear regression t-test and 1var stats all the numbers I need. So I worked out my error, 1.344 times. Now my critical value for 0.75 was that 1.344. I looked at my degrees of freedom again, same thing, 6 minus 2, so 4. Standard error of 3.77. Okay, over the square root of 740.68 minus 1/6, 65.2 squared. Work out the numerator. I like to work out what's in the square root, then take the square root, divide by that number, get about 0.89. Now, we're doing this for beta, so I'll take the b that I got from my regression equation, so what the slope was out of our calculator when we did the linear regression t-test. I'm going to subtract that error. I'll take b and I'm going to add that error. So that error is going to be in those two spots. I think my b from before was 2.55. So subtract, add those two, I get 1.66 and 3.44. So that's saying is I'm 75% confident that my population slope is between those two numbers. Again, I really like this section because it's right before the final exam, and it kind of incorporates some confidence intervals we haven't done in a while, and it's also going to put into some hypothesis tests that we've kind of been doing recently. So try out 1, 2, 3, and 5. They've got a lot of different parts to it, so maybe you just want to try 1 and see how it goes from there. It's got the answers in the back of the book.